light has come. 42nd lecture. We are going to talk about LC driving point synthesis, a continuation of the discussion that we held earlier. You remember last time we talked about Foster 1 and Foster 2, the two forms. Foster 1 was a series connection, whereas Foster 2 was a parallel connection of impedances. And then we said there are two other canonic forms, one is cover 1 and the other is cover 2. And as I said, cover 1 and cover 2 are quite different from Foster 1 and Foster 2. Cover 1 and cover 2 are neither series nor parallel connection. They are in the form of ladder networks, and one arrives at these ladder forms by the following logic. You see, if Z of S is LC, if it consists of LC, then you know that it must have a pole or 0 at infinity. Let us say that Z of S, let Z of S have a pole at infinity, a pole at infinity. If it has a pole at infinity, then obviously I can write Z of S as equal to k infinity S, where k infinity is the residue of Z of S at this pole, plus another function Z1 of S, which as we had showed earlier is also PR and also LC, because real part of this on the j omega axis is equal to the real part of Z of j omega, which is equal to 0. Okay. And therefore, Z1 of S at S equal to infinity, since this is LC and it does not have a pole at infinity, the pole at infinity has been removed, it must have a 0 at infinity. Therefore, Z1 of S has a 0 at infinity. All LC functions must have either a pole or a 0 at infinity. If that is so, then its reciprocal Y1 of S has a pole at infinity. Okay. Now, up to this there was a partial realization like this. We had a k infinity and the rest of the impedance was Z1, partial realization. Now, Y1 of S has a pole at infinity, Y1 is this admittance, and therefore, I can remove this pole and write Y2 of S as equal to, no, let me write Y1 of S as equal to k infinity prime, let us say S plus Y2 of S, that is k infinity prime is the residue of Y1 at S equal to infinity. Okay. Then by the same token, Y2 must also be LC, and the partial realization that I have got now is an inductance k infinity. Then from Y1 you have taken an admittance of k infinity prime S, which corresponds to a capacitor, and the value of the capacitor is k infinity prime. The rest of the admittance is Y2. Now, what does Y2 have at infinity? 0. The pole has been removed, therefore, Y2 must have a 0. In other words, okay, if Y2 has a 0 at infinity, then its reciprocal Z2 has a pole at infinity, and therefore, Z2 can be written as k infinity double prime S, where k infinity double prime is the residue of Z2 at S equal to infinity plus some impedance Z3, and the realization that we have obtained so far is k infinity, then k infinity prime, then k infinity double prime, an inductance, and the rest of the impedance is Z3. Now, you understand the mechanization, the algorithm. That is, what you do is you look at the function. If the function has a pole at infinity, remove it, then take the reciprocal of the remainder function, remove the pole at infinity, once again take the reciprocal of the remainder function, remove the pole at infinity, and go on doing this. So, the ultimate form that you shall get is like this. we shall have an inductance, a capacitance, an inductance, a capacitance, and so on. Now one can argue, this is the most general form. One can argue, suppose the original function z of s, listen to this carefully, suppose the original function z of s did not have a pole at infinity. Then we start with the admittance. If the impedance did not have a pole at infinity, then it must be 0 at infinity. So you take the reciprocal and start with the admittance and admit this capacitance. This will be the first capacitance. The first element will be a capacitance. So this inductance, the first inductance L1 may or may not be present. It shall be present if the impedance function has a pole at infinity. It shall not be present if the impedance function has a 0 at infinity. In a similar manner, the last capacitor, when will this be present?
Has a pole at 0.
Has a pole at 0. Now we are talking of infinity. The behavior at infinity. Can we, you see, at infinity this is short. Therefore this itself, this inductance itself takes care of the pole at infinity.
Yes, sir.
Okay. Now when will this be absent? That is the question I am asking.
When the 0 at infinity. In the end,
The function z, you mean the z of s?
yes, sir.
No. He is quite right. You see, this can be described, the presence or absence of this can be described only in terms of s equal to 0. You see, if this is present, then impedance function, what happens at s equal to 0? This axis is short, this is short, this is short, all of them are short. This is open, this is open, this is open. The last capacitor, if it is there, that means this is also open. In other words, these inductances do not have a path to ground, which means that z of s, original z of s, must have had a pole at the origin. On the other hand, if this capacitor is absent, that is, if there is a short here, then obviously at s equal to 0, z of s has a 0. Is that clear? So this is the most general form. The last capacitor may or may not be present. The first inductor may or may not be present. Otherwise, it is completely general. And this is cover 1. Now, if you notice carefully, what we have really done is,
Sir,
we have made a continued, yes.
Could you please go with the argument of how first inductor won't be present and last capacitor won't be present?
Okay. If the original z of s does not have a pole at infinity, that is, z of 0 is not infinity. I am sorry, z of infinity. Z of infinity is not infinity. If it is infinity, if z of infinity is infinity, then obviously L1 shall be there, and L1 will be the residue of z of s at s equal to infinity. On the other hand, if z of infinity equal to 0, then obviously L1 shall not be there, because the impedance function does not have a pole at infinity. It is the admittance which is a pole at infinity, and therefore we start with C1 instead of L1. On the other hand, the last capacitor, take the situation at s equal to 0. At s equal to 0, all these capacitors are open and all these inductors are short. So what is the input impedance? Infinity. Now therefore Z0 equal to infinity implies that the last capacitor, let us say CL, is not equal to
0. If there is CL, then it will be
if there is CL, what does it mean? CL is not equal to
0.
infinity. If CL is not there, which means there will be a short, that is CL would be equal to infinity. Agreed? Okay. So if Z of 0 is if the original impedance had a pole at the origin, at s equal to 0, if the value was infinity, then obviously CL shall be there. On the other hand, if Z of 0 is equal to 0, this means that CL is equal to infinity. In other words, it is a short. Alright. So, this is a general ladder, series L, shunt C, it is the cover 1 ladder.
So let's suppose this was a driving point admittance.
Suppose there was a driving point admittance.
Instead of ZS, this was a YS function.
Okay. If this is an Y of S, then I look at Y of S. Does it have a pole at infinity? If it has a pole at infinity, then we start with a capacitor. If it has a 0 at infinity, then we take the reciprocal. That is, we go back to the impedance. Alright. So, whether it is impedance or admittance, the same process repeats. You notice that we have focused our attention on a single point in the S plane. And what is this point? The point at infinity. And the synthesis is complete. You go on doing this. You go on insisting that we shall remove pole at infinity from either the impedance or the admittance. We are guaranteed that the point at infinity shall be either a pole or a 0. So, if it is a pole, we will remove it. If it is a 0, then we shall take the reciprocal of the function and then remove it. Now, if you see this process of pole removal at infinity, it just amounts to expanding the function in continued fraction. In a particular manner, we start with highest powers. This continued fraction expansion starts with highest powers in the numerator as well as denominator. Why highest powers? Because we are concerned with the behavior at infinity. It is the highest powers which determine the behavior at infinity. And therefore, all that one is doing, instead of this step by step removal, we can mechanize this by continued fraction expansion CFE starting with the highest powers. Starting with the highest powers. Now, we will come to an illustration of this a little later, but in the same breath, let us discuss cover 2. While cover 1 focuses attention on the point at infinity, cover 2 focuses attention on the point at the origin, that is S equal to 0, because for an LC driving point emittance, S equal to 0 is also a critical point. It is either a pole or a 0. It cannot be anything else. And therefore, what we do is, if we start with a Z of S, if it has a pole at the origin, then we remove it. That is, we write this as K0 by S plus some impedance Z1 of S. If it has a pole at the origin, you may say if it may not. If it does not have a pole at the origin, it has a 0 at the origin. So, we take the reciprocal, admittance. Okay. So, if it is impedance, then all we are removing is a series capacitor of value 1 by K0 and the rest of the function is Z1. Now, what can you say about Z1? Z1 cannot have a pole at the origin because this pole has been removed. So, Z1 must have a
Pole at infinity.
0, no infinity, 0 at the origin, which means that the admittance has a pole at the origin, That means Y1 can be written as K0 prime by S plus Y2, which means that what we are doing is we are removing a 1 by K0, then from admittance we are removing K0 prime by S, which means an inductor in shunt 1 by K0 prime, and the rest of the admittance is Y2. And this process is repeated till we can proceed no further. In other words, we shall end up in an inductor. Once again, this will be the general form. Once again, you see it is a ladder. It is a ladder, but of a different kind, that is series capacitors and shunt inductors. Okay, series capacitor and shunt inductor. The first capacitor may or may not be present. Under which condition will the first capacitor be not present? If the impedance has a 0 at 0. We don't say 0, we say origin, okay, because 0 at 0 it's confusing. Poles and zeros are reserved for the behavior of the total function, where at s equal to 0 is called the origin, okay. Similarly, the last inductor, who will determine whether the last inductor is present or absent? The behavior at infinity, because at infinity all these series arms are short. So if the original impedance has a pole at infinity, then this inductor shall be there. If it is a 0 at infinity, the inductor shall not be there. Is that clear? Okay. Now, so enough of theory. Let's look at examples. Summarizing, we have discussed four canonic forms for synthesis of LC driving point functions: Foster 1, Foster 2, Cover 1 and Cover 2. How do we claim that Cover is also canonic? How do we claim? Yes, you had a question? Pardon me? The question is, how do I claim? I said F1, F2, C1, C2, all the four are canonic. Canonic means the number of elements is exactly equal to the number of specifications. Alright. How do we claim that? We have already shown why F1 and F2 are canonic. Because the number of elements is equal to the total number of specs, that is omega 1, omega 2, etc., and the residues. Okay. How do we claim that C1 and C2 are also canonic? The reason is that every time we are removing a pole, we are reducing the degree of the numerator or denominator by 1. And finally, we will be left with a single degree either in the numerator or in the denominator, which means an inductor or a capacitor, as you saw in both Cover 1 and Cover 2. So as simple as that, the logic is as simple as that, that every time we remove a pole at infinity or at the origin, we are reducing the degree of one of the polynomials by 1, and therefore we are making progress, and the number of elements shall be exactly equal to the degree of the numerator or the denominator, whichever is higher. Agreed? Okay. Now let us take some example. Now one more point before we take example. These are four realizations of the same function, same LC function, four realizations. Now how do you prove, at least verify, that if there is one solution to a synthesis problem, there are indefinite number of solutions? You see, given an impedance function, there is nothing sacred about going Foster 1 all the while. You can go Foster 1 for a few steps and then switch over to Foster 2. You see what I mean? Remove some of the poles in series, the rest of the function you develop in Foster 2. So you get a variation, and this, where you break this step, is your choice. So you can make a combination of Foster 1 and Foster 2. You can make a combination of Foster 2 and Foster 1, that is, start with Foster 2, end up in Foster 1. Or you can oscillate. Start with Foster 1, do Foster 2 for a while, then go to Foster 1 again. And therefore, there is an infinite variety of networks that you can generate. In a similar manner, you can start with Foster 1, and after a few steps you switch to Cover 1. Okay? And all of these shall be canonic. All of these shall be canonic. Foster 1, Foster 2, Cover 1 and Cover 2 are called basic canonic forms. And if you make a mixture of them, for example F1 and C2, it is called a mixed canonic form. Alright? Basic canonic form and mixed canonic form.
So we can make a combination of
any two, and therefore virtually the possibilities are indefinite, infinite number of possibilities. Now let us take some examples. suppose z of s is 2 s square plus 1 s square plus 9 divided by s times s square plus 4. This is the function that is given. The first thing to check is whether it is LC or not. Does it qualify to be an LC? You see, the first critical frequency is a pole at the origin, then at root 1, then at root 4 which is 2, then at root 9. So the poles and zeros alternate. It is a purely odd rational function. Okay? There is nothing in this function which can disqualify it for LC. Therefore, it is an LC function. Alright, without finding the element values. We will find the element values later, but can we, by looking at the function, determine the 4 basic canonic forms? Well, for example, if I want Foster 1, I argue, does it have a pole at the origin? Yes, it does. Okay? The occurrence of S in the denominator shows that it has a pole at the origin, therefore, we must have a capacitor in series. Does it have a pole at infinity? Yes, it has. S to the 4th highest power and S cubed. So, I must have this one also, the inductance. What else shall I have? In the partial fraction expansion, I shall have a term of the form Ks by S square plus 4, which corresponds to a parallel combination of an inductance and a capacitance. So, this must be my Foster 1. Is the point clear? Just by looking at the function. Can I explain it again? I have a pole at the origin, so there shall be a capacitor. I have a pole at infinity because the numerator degree is 4, the denominator degree is 3, and it is only the highest powers which count at infinity. Therefore, there is a pole at infinity, in other words, I shall have this inductor also. Then what do I have? I have a term of the form Ks by S square plus 4 corresponding to this pair of poles, and this corresponds to 2 elements in parallel. This is Foster 1, one inductor and a capacitor. The total number of elements is 1, 2, 3, 4. How many specs are there? 1, 2, 3. No, this is also a spec, the multiplying constant, and therefore there are 4. You see, if this multiplying constant was not there, element values would have been different. Okay, inductors would have been halved and capacitors would have been what? Doubled. Okay. So this is my Foster 1 form.
So is it the original spec?
Isn't the origin? No, the origin is see, origin is not a spec, infinity is not a spec. Why not? Why not? Because origin, I know it must be a 0 or a pole. There is no other way. So origin is not a spec. Alright. Similarly, point at infinity is not a spec. All I am given is, what I need is these 4 numbers, 2, 1, 9 and 4. Just that. Okay. And if the numerator is of degree 4 and the denominator has only a pair of zeros on the j omega axis, S must belong to the denominator. There is no other way. You cannot bring S here. Then the function will not be PR, because the degree difference would be more. Okay. Now to find the element values, can you also do that by inspection? This one, for example, would be, the capacitor would be, the trick is, that's correct. The trick is you put S equal to 0. Then you get 2 into 1 into 9. So 2 into 9 divided by this S, keep this S because this accounts for the pole at the origin, 4. So it is 9 by 2S, 1 by SC. So this 2 by, agreed. Okay. Similarly, the inductance, this inductance, you look at the infinity point, that means the highest powers. Highest powers in the numerator will be 2 times S to the 4th, and in the denominator is S cubed. So it's simply 2. Now, as far as these 2 elements are concerned, you shall have to find K. K is multiply by S square plus 4 and divide by S. So we get 2 S square plus 1 S square plus 9 divided by S squared under the condition S squared equal to minus 4. So let us do that. 2 minus 3, 5 divided by minus 4. Could this be negative? If you get this as negative, then you suspect that you have done some mischief somewhere. Okay, so this is equal to 15 by 2. In other words, what I get is 15 by 2s divided by s square plus 4, and I can write down the element values now. This one, for example, the capacitor.
So shouldn't that be the residue there?
What is residue?
So shouldn't that be the value of the residue?
No, k is not residue, k is twice the residue. Residue is half of k.
So the capacitance value is simply k.
Capacitance value is simply 1 by k, not k, because this is an impedance. You see, it would be s by k. So capacitor value would be how much? 2 by 15. And the inductor value? 15 by 8. I hope you are right. 4 into 2 divided by 15. Yes, okay.
Will you please explain also how we got the K?
How we got the k? Okay. Let me do this. This is written as 2s square plus 1 s square plus 9 divided by s into s square plus 4. We wrote this as k0 by s plus k infinity s plus some ks divided by s square plus 4. So how do I find k? I multiply both sides by s square plus 4. I multiply both sides by s square plus 4. Then on the right hand side I shall have ks. I want to find k, so I divide by s. Then I put s square equal to minus 4. In the right hand side, this term will be 0, this term will be 0, because I multiplied by s square plus 4. It is only this that shall remain. So I multiply this by s square plus 4, s square plus 4 cancels, and divide by s. So k is therefore equal to 2 s square plus 1 s square plus 9 divided by s squared under the condition s square equal to minus 4. This is what I did. Okay. Now before I pass to Foster 2, we are going very slow. Okay. We are going very slow. Before I pass to Foster 2, can I ask you this question again? I did ask you, but I want to bring out a point. Suppose we had here a very large constant, let's say 159.38. Then instead of handling such large numbers with fractions and all that, we could have simply ignored it and obtain a realization of this with nice numbers. Finally, after I get the network, I can change the element values. How do I change the element values?
Multiply k with inductor and divide capacitor by k.
That's right. So the multiplying constant will multiply the inductors and divide the capacitors. This is called scaling. S-C-A-L-I-N-G. That is the principle, extremely simple principle. It is that if you know the synthesis of Z of s, then you also know the synthesis of Kz of s. All that you have to do is to change the inductors, multiply them by k and divide the capacitors by k. Now instead of an LC network, if I had RLC network, okay, then what would have happened to the resistors?
So
multiply the resistors by k. Suppose I know the synthesis of Y of s, some admittance, and I want to find out the synthesis of ky of s. All that I do now, multiply the capacitors by k, divide the inductors by k, and resistors, if there are any, divide by k. This is called, as I said, scaling. And many a times the numerical calculations, particularly in very complicated functions, one does that. One takes out a constant such that the rest of the numbers are nice numbers to deal with, and then finally change the element values. Do it once only. Do not make your life miserable throughout the calculation. Okay. Now let's look at Foster 2. Our function was Z of s equal to twice s square plus 1 s square plus 9 divided by s times s squared plus 4. For Foster 2 we have to take the admittance. Okay, Foster 2 is a parallel connection, so we take the admittance. Y of s is equal to s square plus 4 divided by 2 s square plus 1 s square plus 9. The admittance, fortunately or unfortunately, has no poles either at either external critical frequency. You see, at s equal to 0 it is a 0, at s equal to infinity it is also a 0, and therefore I can immediately draw the form of the network. What will be the form of the network? Just two LC networks, two series LC networks in parallel. Isn't that right? Is this okay? How do I get that? This function has no pole at infinity, so there is no shunt capacitor. This function has no pole at the origin, so there is no shunt inductor. Alright, and there are 4 specifications. There must be 4 elements. The partial fraction expansion of this would be k1s divided by s square plus 1 plus k2s divided by s square plus 9, and each of them will give you a series LC circuit, each of them, and therefore there are 2 LC circuits in parallel. Is that clear? No single inductor, no single capacitor. All right. To find out K's, y of s is s times s square plus 4 divided by 2 s square plus 1 s square plus 9. This is equal to k1 s divided by s square plus 1 plus k2 s divided by s square plus 9. So k1 we multiply by s square plus 1. With a little bit of practice you do not even have to write this, or you write in abbreviated form. For example, I do not write this function again. What I do is s times s square, the numerator shall remain the same.
3 by 16.
This would be twice s times s square plus 9. No.
3 by 16.
Okay. Under the condition s square equal to minus 1. So 3 by 16, that is correct. K1 is 3 by 16 and K2 5 by 16. Doesn't look all right to me. Yeah, okay. Minus 9 plus 1, 5 by 16. And therefore, write this y of s 3s by 16 s square. Now I am giving you a trick. I am writing this denominator 16s square plus 16, okay, so that my element values are obvious, and this plus 5s divided by 16s square plus 144, and therefore, okay, and therefore I can write y of s. With a little practice you don't have to do this, but to start with it is not a bad idea to do this. I divide both by s, 3s, that is I make the numerator as 1, then I get 16s by 5 plus 144 divided by 5s, and the element values should be obvious.
So 16 by 3 and 3 by 16.
This is 16 by 3 SL and 1 by SC, so this is 3 by 16. One of the verifying features is that the product of these two must be the reciprocal of omega 1 squared. Okay, it's a series resonance circuit, and this is the frequency of resonance. Omega 1 squared is 1. Here the product should be equal to 1, and here 16 by 5, and this would be 5 by 144. The product L2C2 must be 1 over omega 2 squared, and omega 2 squared is 9. All right. Therefore, the product of these two is indeed 1/9. That takes care of Foster 2. There are exactly 4 elements. You have a question? Okay.
Sir, this relationship is for this particular.
No, for any, even in the parallel LC, Foster 1. In Foster 1, the product of the two, inductance and capacitance, shall be 1 by omega naught squared. Okay. That is a verifying feature. Let us go back to the impedance function Z of S equal to 2 S squared plus 1 S squared plus 9 divided by S into S squared plus 4. Now we are asking for cover 1. The question this is a crucial step, and one must be very careful. First you ask the question, does the function have a pole at infinity? Yes, it has. So we can start continued fraction of Z of S. If it does not and you start blindly, you shall get nonsense results, and immediately you should go back and correct yourself. Okay. Here now this factored form is of no use now, so we must reduce it to a polynomial form, and you can easily see that this is S cube plus 4, and in the numerator is twice S to the 4 plus S cube plus 4s, all right. In the numerator 20 S squared plus 18. We could have done away with 2, we could have, but 2 is a nice number, it does not really affect us. So let us keep it. Now we start continued fraction expansion, 2s to the 4 plus 20 s squared plus 18, and as I said, to avoid going like this, we will bring the remainders here, and the first quotient is 2s, and this is an impedance. You must go ahead and identify the dimension 2s, so we get 2s4 plus 8s squared, agreed, and you bring here 12s squared plus 18, that divides s cube plus 4s, the quotient is s by 12, and this is an admittance y. So s cubed plus 18 by 12, that is 9 by, pardon me? 3 by 2s, okay, 3 by 2s. The remainder is 5 by 2s, that divides 12s squared plus 18. So the quotient would be 24 by 5s, and this is an impedance. 24 by 5s, is that okay?
Yes,
it seems okay. Okay, 12s squared, remainder is 18, and all that you have to do now is 18 divides 5 by 2s, so you get 36 by 5s. I hope I am right. Oh, 5 by 36. S 5 by 2s and 0. This is admittance. What is the dimension of this?
Impedance.
No. 0 by 18. You see, isn't it? This quotient plus remainder divided by the divisor.
So this is
This must be admittance. It has to be. If it was impedance, then 0 impedance means short circuit. So the last element, what is the last element here? Capacitor. It is an admittance. So our network becomes this. I have a 2 Henry inductor because we started with an impedance, then 1/12 capacitor, then 24 by 5, and finally 5 by 36. The rest is 0 admittance, which means infinite impedance, that means open circuit. Alright, it has to be that way, there is no other way. There are exactly 4 elements, and the last element is a capacitor, because what is the reason that this is a capacitor? Because the function had a pole at the origin. Don't say why you have open circuit. You see, the last device, the remainder, this is 0, and so 5 by 2 by 18, 5 by 2s divided by 18, this is the division that we have performed here. This is equal to 5 by 36s plus 0 by 18. If this is admittance, this must also be an admittance, and this 0 admittance means an open circuit. Had it been an impedance, then it would have been a short circuit. Okay? Alright. The point that I was mentioning is, the question that I was putting is, why is the last one a capacitor?
So you couldn't have got anything else.
Pardon me?
You couldn't have got anything else but 0 in case of.
Of course, of course. It could have ended in an impedance 0. Then you have to put a short circuit there. For example, if the function to start with, there is a pole at the origin. Alright, that is why the last element was a capacitor. If it did not have a pole at the origin, then the last element would have been a short circuit. That is, the last element would have been an inductor. That means instead of a capacitor we would have a short circuit. It is important to understand this. After a while it will become routine, after a while, but you require a little bit of practice. Now let us go to cover 2. Now cover 2, our function is z of s equals to s cubed plus 4s 2s4 plus 20s squared plus 18. Cover 2, as I said, focuses attention on the point at infinity. It focuses attention on the point at point at the origin. Cover 2 focuses attention on the origin, and therefore what we do is we remove terms like k0 by s. In other words, our focus now shall be on the lowest powers, not on the highest powers. And to be able to remove a term like k0 by s, obviously continued fraction expansion has to be started with lowest powers, not highest powers. Highest powers gives cover 1, lowest powers gives cover 2. The question that one should ask is, does the given impedance, given function have a pole at the origin? If it has, then you start continued fraction expansion. If it does not have, then you take the reciprocal and then start continued fraction. Here we shall write it, we shall have to write it like this, alright, starting with the lowest powers, and the numerator 18 plus 20s squared plus 2s to the 4th, alright, and we have to continue.
Can you please explain what you told about pole at origin?
Pole at origin, okay. Before starting any continued fraction expansion, you have to ask, is the function prepared for that particular continued fraction expansion? For example, in cover 1 we asked the question, does z of s have a pole at infinity? If it does not have, then you cannot start continued fraction expansion of z of s. You have to take its reciprocal and then start. Here also we ask the question, does z of s have a pole at the origin? Yes, it does. It has a pole at the origin. That is why we could start continued fraction expansion of z of s.
But at s is equal to 0, the function is 0.
Function is infinity.
18 by 0.
18 by 0.
That is precisely the point. Therefore, we can start continued fraction expansion with z of s, but now since it is cover 2, our point of attention is the point at the origin, we start with the lowest powers. And our first quotient becomes 18 by 4, which is 9 by 2 s. S is in the denominator now. Why do we start with it? Because cover 2, in cover 2 we want to express this as k0 by s plus some other function z1. How can we get k0 by s unless we start continued fraction expansion with the lowest powers? You see, highest powers always gives you quotients of the form k times s. You have to get k by s, and therefore you must divide a constant by the s term. Okay, this is the mechanization. But even if you do not know continued fraction, cover 1 is not very difficult. because it simply means removal of poles at the origin. If the function has a pole, remove it. If the function does not have a pole, take the reciprocal and remove it. But this is the mechanization. Okay. Let us continue this continued fraction expansion. 4s plus s cubed 18 plus 20s squared plus 2s to the fourth. The first quotient is 18 by 4s, which is 9 by 2s, and the dimension is impedance. I get 18 plus, what do I get here? 9 s squared by 2. You must not forget the power, s and s cubed, so s squared by 2. This would be 40 minus 9, that is 31 s squared by 2 plus 2 s to the fourth. This divides 4s plus s cubed, and I get 8 by 31s. This is an admittance. So I get 4s plus 16 by 31 s cubed. Is that okay?
15 by 31 is.
So I get 15 by 31 s cubed, 31 by 2 s squared. Numbers are getting nasty, but keep it as a fraction as long as you can, all right, as long as you can, because as soon as you shift to decimals, you are bound to ignore later part of the decimal, and then this will create errors. Finally, you may not get 0. You may get 10 to the minus 4 or 10 to the minus 5, depending on how much error you committed. So in numerical calculation, keep it as fractions as long as you can. All right, what do we get here?
961 by
31 squared divided by 30. S is in the denominator and this is an impedance. So 31 by 2s squared. Fortunately, it's not too bad. Our last remainder is 2s4 divides 15 by 31s cubed. So I get 31 into 2 divided by 15s. No.
So 15 by 62.
15 by 62s, and this is an admittance, so 15 by 31s cubed, and the remainder is 0. This 0 is once again admittance. So my final network becomes, we start with a capacitor 2 by 9, the next one is an inductor, value is 31 by 8, 1 by SL. The next one is a capacitor 30 by 31 square, 961, okay, and the last one is an inductor 62 by 15, and that completes the job of cover 2. Pardon me? The rest is open circuit because the remainder is an admittance which is equal to 0. Now, of these 4 networks that you have obtained, which one do you think you will prefer? Why? Smallest capacitors? Now one has to be careful. You see, in Foster, in cover 2, the total capacitor is 2 by 9 plus 30 by 31 square. In cover 1, it is 1/12 plus 5 by 36. In Foster 1, let me see. Foster 2, 3 by 16 plus 5 by 144. And what was Foster?
2 by 15 and 2 by 9.
2 by 15 and 2 by 9. Now, before I get you involved in this calculation, let me point out that it is not just the total capacitance. Capacitance large value is not a problem. The problem lies in LC networks in particular, and almost all analog filters that are used in practice are required to be LC, required to be if it is a passive filter, because a very simple reason. Our power is very precious. We don't want to lose it. If there are resistances, they will absorb power, and therefore as it proceeds, as the communication channel, as the signal proceeds on the communication channel, it gets attenuated. Not only attenuated, it gets distorted also. Alright. So, most of the telephone filters, telephone channel filters for example, even with digital telephony, filtering at crucial points are done by analog means, and you require inductances and capacitances. The point at stake is not just the total capacitance, because capacitance is not a very crucial element. A crucial element is the inductor, particularly at low frequencies. At very high frequencies, radio frequencies, broadcast frequencies, or the short wave or the broadcast band, well, it's not a problem. Capacitor inductance also is not much of a problem, but at low frequencies inductance is a problem, and there one has to bother more about the inductor Q, because you cannot make a large inductor without a large resistance. Alright, and as soon as you introduce a large resistance, well, the current squared multiplied by that resistance, you just have no way to obviate that. That amount of power shall be dissipated, and therefore what I am saying is, in the realization, it is not just the total capacitance. Maybe the total inductor is important, or the individual value of the inductor. Maybe in one of these realizations there is required a very large inductor, and you would not like to make that kind of an inductor, because you know, to make, let us say, 1 Henry inductor, you require very large space. The number of turns is required to be very large, and then 1 Henry inductor, if you do not have iron as the core or ferrite as the core, then you might have to use this whole room to wind a 1 Henry inductor, okay, and that is not a practicable solution. That is not a so you use cores, you use special kind of wires and other things, and if you use a core, then you have to bother about many other things. It's not just ohmic loss, there are other losses, AD losses, okay. So inductor is a nuisance as far as
large inductor, won't there be more of mutual inductors?
That is another problem. As soon as you use an inductor, a capacitor, there are static problems, there is coupling in electric field, but inductor coupling is more of a menace, because as soon as you have an inductor, well, it's creating flux, and if this flux terminates on a nearby equipment, well, it's going to destroy the functioning of that equipment. In addition, if there is a mutual inductance with the neighboring machine, and therefore the performance of this particular machine is also going to be at stake. So it's not just inductors, it's not just capacitors, it's the total structure that is important, and it depends on what you can realize in practice. Number 2, 31 by 8 or 62 by 15. 62 by 15 is more than 4 Henry. Who is going to make a 4 Henry inductor for you? Well, these are all normalized values. You don't require a circuit in which the resonance frequency is 1 radian per second. It will possibly be in the kilo or mega range, and therefore these values shall also be scaled down accordingly. An inductor of the range of 1 millihenry is perhaps the highest that one uses in practice in filter circuit design, whereas in machines and power systems, maybe you use larger inductances, but in communication, telecommunication, you don't use more than a millihenry. Similarly, capacitor values are limited to microfarads. If you go beyond microfarads, then there is a practical problem. What is the problem? Size is one, and leakage. The higher the value of the capacitor, the more is the leakage, because you see between two, let's take an aluminum foil which acts as the plate. Now between two aluminum foils you have to put an insulator. That insulator is not a perfect insulator, that is the leakage, and that as the value of the capacitor increases, the area through which leakage can occur also increases, and therefore the conductance G decreases. No,
Resistance
increases. Resistance is in shunt, so if it increases it is good. Conductance increases and therefore resistance, shunt resistance decreases. So these are the practical values, and life is a compromise. Electrical engineering is no exception, you have to make compromises. More tomorrow at 10 o'clock.